All right, today we are diving into an idea that is, well, it's truly audacious. We're talking about building a time capsule to store information inside the sun. Yeah, you heard that right. It's a concept that pushes the absolute limits of engineering and physics, and it all kicks off with one simple, totally mind-bending question.
So just imagine this for a second. What if you could send a message to our sun and have the star itself hold on to it for years, maybe even centuries, before echoing it back out into space? And no, we're not talking about, carving initials onto its surface. We're talking about turning the sun's own fiery plasma into a kind of natural hard drive, a stellar time capsule.
Now, the source material actually lays out two incredible ways this could theoretically work. First, there's the plasma echo capsule, which would use the sun's own magnetic fields to trap a signal, almost like an echo bouncing around in a canyon. Then you've got the time-dilated probe. This is a wild one. It would use a solar flare to basically slingshot a probe to near the speed of light. Thanks to Einstein's theory of relativity, its internal clock would slow way down, creating what is, for all intents and purposes, a message from the future. For this explainer, though, we're going to focus on the plasma echo capsule, because, believe me, the challenges there are more than enough to boggle the mind.
Look, this isn't about breaking the laws of physics, it's about hacking them. The whole idea is to use the sun's own environment, all that plasma, its magnetic fields, its raw, insane energy, as a component of the time capsule itself. But, and it's a big but, to do that, you have to get incredibly close.
So, you might be asking, why not just shoot a powerful signal from Earth? Well, the source explains that over that vast distance, the signal just spreads out and gets weaker and weaker. It's a problem called geometric dilution. Think about it like a flashlight. The further you are from a wall, the dimmer and bigger the circle of light gets. Plus, the sun's chaotic plasma would just scramble that signal into useless static. No, to make this work, you have to go right to the source, the solar corona. And that means surviving a literal inferno.
Calling it a furnace is a massive understatement. Trying to send a probe into the sun's corona to do something this complicated is easily one of the greatest engineering challenges you can possibly imagine. It's like the environment is actively trying to melt, fry, and scramble any piece of tech we send its way.
First off, there's the heat. The solar corona is a mind-boggling 1 million degrees Celsius. And what's really bizarre is that it's way, way hotter than the sun's surface that we can see, which is just a cool 5,500 degrees. It's one of the great mysteries of solar physics, and it makes for an unbelievably hostile place to visit.
Now, despite that insane temperature, the corona is technically a near vacuum. It's way less dense than the air you're breathing. But these aren't just normal particles. Oh no, they're a superheated plasma, a chaotic sea of charged particles that creates this electromagnetic maze. And that, right there, is where the real problems start.
This brings us to a fundamental rule of this environment, the plasma frequency cutoff. You can think of it like an invisible force field. If the frequency of your radio signal is too low, the plasma just bounces it right back, like a mirror. The source even gives us the formula that tells you exactly what frequency you need to punch through that wall, and it all depends on how dense the plasma is at that very spot.
And the problems just keep piling up. That plasma is like a raging storm. It's so turbulent, it could just rip your signal to shreds. Any energy you manage to pump in just vanishes into heat almost instantly. And you need a ridiculous amount of power just to make a tiny whisper that could be heard over the sun's constant roar. It is, in short, a brutal, brutal place for any kind of technology.
Okay, so how in the world do you build a machine that can survive all of that? Well, you're going to need a shopping list filled with some of the most exotic, most resilient materials ever conceived. Let's take a look at what it would actually take to build this star probe.
For the all-important heat shield, you'd be looking at materials that have already been proven on missions like the Parker Solar Probe. We're talking carbon-carbon composites, which are incredibly strong in light even when they're scorching hot. And then there are carbon phenolic ablatives. These are amazing. They're designed to literally burn away, layer by layer, carrying the extreme heat away with them. They basically sacrifice themselves to protect the spacecraft.
So what about the parts that actually have to poke out and face the plasma head-on? Well, the emitters that send the signal would need to be made of something like tungsten, which has one of the highest melting points of any element. The insulators would have to be advanced ceramics like boron nitride. And any windows on the probe, they'd need to be made of materials like pure sapphire. Yeah, the same stuff in high-end watches, but used here for its incredible toughness and transparency.
And the electronics inside have to be just as tough. Your standard silicon chip, it would fry in a fraction of a second. So instead, you'd have to use special materials like silicon carbide and gallium nitride that can operate at much, much higher temperatures. You'd also need radiation-hardened processors that can withstand the constant bombardment, huge capacitors to deliver the powerful energy bursts needed, and fiber optic cables to move data around, since they're totally immune to all that electromagnetic chaos.
But having all the right materials is only half the battle. You can't just put a star probe together with nuts and bolts. The construction techniques themselves have to be just as advanced as the materials, involving processes that honestly sound like they're straight out of the distant future.
So to join these different exotic materials together, you'd use a technique called vacuum brazing. It creates this perfect molecule-to-molecule bond between metal and ceramic that can handle the intense heat. You'd also use additive manufacturing, which is basically 3D printing with metal, to create these incredibly complex internal cooling channels that would be impossible to make any other way. And finally, you'd have a whole network of heat pipes acting like the probe's circulatory system, constantly pumping heat away from the sensitive bits to radiators on the cooler, shaded side.
And all of this points to the core design philosophy: survive no matter what. You simply can't expose the entire probe to the full fury of the sun all the time. So the most sensitive parts, like the antennas, would be tucked safely away behind that massive heat shield for most of the trip. Then, only at the perfect moment would they deploy out into the corona to do their job, before quickly retreating back to safety.
And that really is the bottom line. This quote from the source material just says it all. You must be basically in the coronal environment to have any realistic chance. There are no shortcuts. You can't do this from a safe distance. You have to be right there, a participant, in the heart of the sun's atmosphere. And that's what makes this mission so incredibly difficult and so potentially revolutionary.
Okay, so after all that talk of impossible heat and materials from the future, let's pull this concept back down to Earth for a second. How would you even begin to test an idea that's this ambitious? Well, the source actually lays out a pretty practical and logical approach.
First things first, and this is super important, this is not a time machine. The source is very clear on this point. This isn't about sending information into the past, a concept called retrocausality. You are simply storing energy in the plasma for a while to create a delayed echo. Think of it as a time capsule, not a time telephone to call your past self.
The roadmap to actually get there is grounded in real-world science. You'd start with massive supercomputer simulations to model the sun's plasma and try to find stable little islands where an echo could actually survive. Then you'd build a sun in a jar, a lab experiment to test the basic physics and the hardware. And only after all that would you even think about launching a small Pathfinder satellite to get real data from the corona, which would then pave the way for a full-scale mission.
Okay, sending next week's lottery numbers to the past is definitely off the table. But this whole concept leaves us with a really profound scientific question. If we could actually create these echoes in the sun's plasma, what could they teach us about our own star? What secrets about turbulence, about magnetic fields, about how energy moves, what secrets are just waiting to be discovered? Not by looking at the sun, but by listening to its echoes.